Hello, I am Nicholas Clark here with
Aaron Roper.
And this is your Physics World News. Today, we are doing a lab. No.
The lab is about horizontal distance versus horizontal velocity. Well, how are we going to test that? Nick, how do we test that?
Well, first off, the purpose of our experiment is to determine the graphical and mathematical relationship for the horizontal velocity and the horizontal displacement the ball traveled through the air after coming down an inclined ramp.
So basically what we do is we have a ramp and then we roll the ball down and then it hits a little horizontal surface so that it doesn't have vertical velocity. So it goes across the horizontal surface and it shoots off the edge of the table. And what we're measuring is how the velocity as it goes off the table is...
And that is our independent variable, the velocity.
But yeah, the velocity is the independent variable. How that affects our dependent variable, which is how far it travels from the table. As far as our materials go, we have a few. We have the ramp, we have the ball, we have the meter stick, we have the carbon paper on the ground, and we have a timing device. Also in this lab we use a lot of tape.
See the vegetable man in the vegetable van with the horn that's honking like a mariachi.
We have the ramp.
Nice place.
We have the ball.
Okay.
We have the meter stick. We have the carbon paper on the ground. And we have a timing device.
With plastic bags, walking to the church.
The ramp is about 120 centimeters long, and what we do is we tape a meter stick to the side of it.
Do we do a thumbs up? I can do it someday.
We also had the ramp at a 3 degrees angle, which was our constant incline.
The ball weighs 66.7 grams, and it is 2.5 centimeters across.
Which is 0.025 meters.
Heck yeah. It goes student groups,
Lover Pro experiments.
probes, and sensors,
One gate timer.
and that's how you get the velocity using one probe. Next, you have to record the displacement where the ball landed past the table, or where it landed on the carbon paper.
And make sure the angle of the ramp hasn't changed. That is a constant variable, and so it needs to stay constantly 3 degrees for every trial.
The release point of the ball has to be moved back by 0.5 centimeters each time. So that's so you can have a number of trials.
And you would also take each trial twice in order to have an average to make your data more accurate.
You repeat the last 5 steps that we said, and then you finish your lab and you clean up and you go home.
And that's the procedure. Now let's go on to, what does my little paper say? Raw data. Raw data.
Done. Finally. Oh my gosh. Took forever. Next comes the evaluation of data. Well, for evaluation of data, we have to take some sample calculations. First off, we had to take the average of the horizontal velocity. So what you do is you take the multiple trials, you add them together, and you divide by the amount of trials that you used. So, for instance, if you had 0.744, 0.754, and 0.754 again, you add them all together and you divide by 3, and your average becomes 0.751.
Next, we're going to do horizontal displacement average. So like Aaron had previously said, you take all the times you had done one trial, you add up those values, divide by the number of times you did it, that gives you your average. Thus, if your horizontal displacement was 0.25 meters, Another one was 0.26 meters. Another one was 0.26 meters. Divide by 3, you get 0.256 meters. So that would be your average displacement in meters.
However, if you were using significant figures, that would be rounded back up to 0.26. When you are converting centimeters to meters, which is our next sample calculation, you have to take the decimal point and you have to move it 2 places to the left. So say you have 25 centimeters, you move the decimal point 2 places to the left, and your result is 0.25 meters, which makes sense because there's 100 centimeters in a meter.
So now we need to do the 5% rule, and that is to distinguish whether we actually need our b-intercept or not. Our b-intercept is where the graph crosses the y-axis. You're going to take your b-intercept, which was 0.3909, you're going to divide that by your highest y value, which is 0.442, and you're going to multiply that by 100, and that would give you 8.84%, and that is greater than 5%, and so you're going to keep your y-intercept.
Now it's time to sum everything we've learned up into a conclusion. First of all, the horizontal distance is directly proportional to the horizontal velocity. We found this through the graph, which we saw in the lab. The math model of our lab was x equals 0.363 seconds velocity minus 0.03909 meters.
The meaning of the slope was the time it took for the ball to fall. After using the 5% rule, we came to a percentage of approximately 8.8%, which is higher than 5%, so we kept a y-intercept.
The meaning of the y-intercept would be when the velocity in the x direction is 0, the distance it will travel is 0.03909 meters. The generalized math model is x equals t times v of x plus x of o, or our initial position.
New terms that we have learned are the usage of meters per second as just being seconds.
What you do to find seconds from meters per second is you multiply by the reciprocal and the m's cross out, and you're left with seconds over 1, which is seconds. For the application problem, doing all the math, we think that if we drop the ball from 19 centimeters on the ramp, then it will result in a velocity of 0.5. 19 centimeters.